Hello, my favorite Gen Chem 2 class. I am so excited by our next topic. It's one of my favorites, Hess's Law. We're going to continue our thermochemistry, and we're going to get just a little bit deeper with our thermochemistry table, that thermochemical table that we handed out. So why don't you hit pause for a second and go grab that table? We're going to need it. Okay, I wanted to connect to textbooks. Again, we're going zero textbook in this class, so I really like this first link. It's got a really great chapter on enthalpy. Our Hess's Law is about 3/4 of the way through that chapter. It's kind of towards the bottom, so you have to look for it just a little bit, but I really like that book. And then there's also some Hess's Law on our Chemistry Libre. So we've got two different sites that have some connections there. And then of course in any textbook, if you've got an old textbook that you've got your hands on, which is awesome, you'll find Hess's Law in that thermochemical chapter as well. So I want to actually pose a question about our thermochemical table. Do you ever wonder with our formation reactions, well, how does that end up on the table? So this is kind of a two-part series. Our calorimetry was first, and then now this one is second. We're getting just a little bit deeper with where those values are coming from on our table. So let's give an example. I just want to give an example. Let's start by saying, you really have in your heart this formation reaction to make NO2. And you sit down and you know your formation reactions. So we're going to take nitrogen and oxygen and we're going to make NO2. We're going to go ahead and balance that. Okay. And this is what you're going to go and you're going to find this on the table. You would absolutely find a value on the table for your NO2. And this is your goal. Okay, awesome. But then you happen to notice, well, wait a second. If I'm looking at a formation reaction on the table, why isn't it just NO2? Why is there a whole list of possible options for our combinations of nitrogen and oxygen? There's a whole bunch of them. So that should get you thinking, well, wait a second. Which one is right? Holy crap. Where do they come from? Because in theory, if I were to go to the lab and use calorimetry and take nitrogen and mix it with oxygen, well, son of a motherless goat, which one am I going to make? Am I going to make this one or any number of these? Do you just go ahead and close your eyes and find your meditative space and just think hard on the one that you want and hope that's the one that you get? No, unfortunately, all of this is up to Mother Nature, and it's not actually up to you. So how do you then have all of those options as formation reactions on that table? Well, this is where Hess's Law comes in. This is awesome. This is where a large portion of that thermochemical table is actually coming from. Not every combination of elements makes exactly that product that's listed on the table. Now, I'm going to add to this example, but in order to understand it, I want to go back for a second and refresh this definition of a state function. Our state function we looked at in our very first video on a beaker of water, and we talked about that internal energy. Did it matter if our beaker of water was frozen last night or boiling this morning? No, it didn't. It mattered the state it was in. In fact, we gave it this nice definition that it is path independent. And we're going to use that definition again today and just grow it in order to be really practical. I think the ice one, that beaker of water one makes sense. Okay, the actual internal energy in that beaker is really dependent on the state it is sitting there in front of you when you're studying it. But how does that apply to our thermochemistry? How does that apply to actual reactions? Well, it turns out we're going to add to this idea our enthalpy is also a state function. And it turns out it is also path independent. So let's give that a frame of reference. What does that mean? That means you don't have to form your compounds in one reaction. You can have several steps in that process, and it does not matter. All right, let's put a reference on that. Let's go back to our nitrogen and our oxygen example. So let's say this is the one that we see on the table, okay? And this on the table is 68 kilojoules per mole, okay? Awesome. Well, what really happens to form that, let's scroll down just a little bit. If I mix nitrogen and oxygen, you don't directly make NO2. In fact, what Mother Nature does is if you mix nitrogen and oxygen first, you make NO. Those two smack into each other and they make NO. Okay, well, hang on a second. That's on the table also. Okay. All right, that is on our table. And then it turns out that that NO turns right around and smacks into another oxygen, and that makes NO2. This is Hess's law. Our actual enthalpy as a state function, meaning it's path independent, this overall process is what we'll see on our table. But it doesn't matter that it's happening in 2 steps. Okay, now we still have to follow some rules for that, right? So this first step, our overall goal step, is already on the table. That's a formation reaction. And then this second step here is already on the table. That's a formation reaction as well. But what if you wanted to study that final product? Okay, in other words, where did this number come from? Well, if we had data for this, we could figure that out. Or if you have both of the numbers that I've given you on the table, couldn't you also actually figure out what this is? So Hess's law is one big summation, one big balancing act. In fact, my nitrogen and oxygen, as soon as they collide and make this NO, Mother Nature turns right around and uses it. So I get to cancel that. Okay, now let's look at this overall process. You're left with nitrogen and 2 oxygens on your reactant side, and you're left with your product of NO2 on the product side. Now, we already know this number from our table, but also where did that come from, or what is this middle number? These have to add up as well. So it turns out that this middle process has to be negative 112 so that our overall process gives this number. So Hess's law actually can be used for several things. Number one, we can start to get different compounds from our formation reactions. That's why these numbers are quite different, right? This formation number is quite endothermic, and this one isn't quite as endothermic. But we can also study those intermediate reactions and have a way to get to this information also. So what I like to do for Hess's law is always keep in mind our goal, and we are going to treat these like the mother lode of balancing reactions. So grab your yoga pants and light a candle, because not only are we going to balance our reactions, we're going to balance several at a time. And remember, we're not balancing just our overall reaction. We have to balance that math as well. So this is one massive summation. So the important take home for Hess's law is that in your overall reaction, so I will call that my goal reaction, it doesn't matter how many steps it takes to get there. It matters that whole overall goal process. All right, let's use Hess's law again. let me pose another question for you. If you look on your thermochemical table and you notice that there's carbon graphite and that there's carbon diamond. Okay, awesome. But yet everything on our table uses that in a reaction. But what if you actually wanted to know if you wanted to convert carbon graphite to carbon diamond? I wonder how much energy that would take. I wonder what that enthalpy would be. Well, you can't write a formation reaction for that. That's two forms of elemental carbon. How in the world could you get to that information? Well, Hess's law works in many ways. We can use that summation to actually cancel. As long as we can cancel intermediates, we can end up with an overall process of converting those two carbons. We can go from carbon graphite to carbon diamond and figure that out. So let's just write out for a second. What am I even talking about? It seems like I'm not making sense. Let's try this. I do see on the table that I can take carbon graphite and I can react it with oxygen and make carbon dioxide. Okay? That we have data for. That is known. Let's write that down. That formation reaction is exothermic, 394 kilojoules. Okay. Holy crap, right underneath it, I have carbon diamond reacting with oxygen and making CO2. And that is also on our table. And that is exothermic by 396 kilojoules. Okay, now how can I use this to actually convert carbon graphite to carbon diamond? Okay, I start all of these with my goal. And why? Because I need this process. This is like one big summation. My overall process, I want it to say carbon graphite to carbon diamond. Done. So that means that I have to have carbon graphite on this side so I can keep it. So I'm going to write this reaction in this way. And we already know that data, 394. Okay. But now here's the kicker. Carbon diamond in this reaction is on the reactant side, but I want it on the product side. So we already know from thermochemistry, hold our seats. Isn't this number the same value, different sign if we're going backwards? Remember in our energy diagram, we drew this forward or backward. The value is the same. It's the direction that changes. So shut the front door. I'm going to write this thing backwards. We are going to take our CO2 and break that up into oxygen and carbon diamond. And now what do we do with our sign on our number? We flip it. Okay, that's a kilojoules. All right, so now anything that is on the reactant side and the product side equal, we get to cancel. So right away, oxygen, done, canceled. Carbon dioxide, done, canceled. And look what we have in our overall process. Carbon graphite is left, carbon diamond is left. Perfect. That is our goal statement. Okay. Now what do we do with the math? Well, it's a summation. So we're left with a positive 2 kilojoules. So if we wanted to convert carbon graphite to carbon diamond, it would require 2 kilojoules in order to do that. So our Hess's law can actually give us all kinds of information. It doesn't matter that this process in theory could happen in 2 steps or 3 steps or 4 steps. What matters is that this overall process is our goal statement that we're looking for. So in nature, who knows how carbon graphite turns into carbon diamond? Does it go through carbon dioxide or not? It doesn't matter. We made it and then we used it. And so that process is independent. Okay, so let's take this example and let's get just a little sassier. What else can we do with Hess's law? All right, I've given us a goal statement. Let's see if we can't use our thermochemical table using only formation reactions. Okay, let's use a series of formation reactions and actually solve for this overall reaction. Now, I want to show you my process for these because Hess's law, when you first start it, might be just a little bit tricky, but after we do a couple, they're actually just flat out fun. So I figure out what my goal is. Okay, this is going to be the goal. And then I know that I'm going to put together a whole series of reactions and end up with that goal as is. So I just go right ahead and I write the goal.